All right, hello everyone, and welcome to the seminar number 73. This is Kirill Belashenko from University of Nebraska, and I'm happy to introduce our speaker today, Professor Binek, who is my colleague here at UNL. Dr. Binek is Charles Bessey Professor of Physics at the University of Nebraska, as I said. He received his PhD in 1995 at the University of Duisburg-Essen in Germany, with a thesis that earned him an annual award of the Duisburger Universitätsgesellschaft for an outstanding PhD thesis. This was followed by habilitation in 2001 with research experiences in France and Japan. And then he joined UNL as assistant professor in 2003. He received an NSF Career Award and a 2007 Sigma Xi Outstanding Young Scientist Award. He was fully promoted by 2015 and was just recently named the Charles Bessey Chair Professor. Since 2019, Dr. Binek serves as director of the Nebraska Center for Materials and Nanoscience, and also as director of the Nebraska Nanoscale Facility, which is one of the sites of the NSF-funded National Nanotechnology Coordinated Infrastructure. In 2021, just this year, he became the scientific director of the NSF-funded Center on Emergent Quantum Materials and Technologies, or EQUATE. If there are people in the audience from the Nanogune Research Center in San Sebastian, you may remember that in 2013, Professor Binek was there as a visiting professor, and he also became an Aker Basque Fellow of the Basque Foundation of Science at the time. Christian's research interests are in magnetic interface effects in nanostructured materials, with emphasis on electrically controlled magnetism, spintronics, and quantum materials. He is an author of well over 100 peer-reviewed publications, a book on Ising-type antiferromagnets published by Springer in 2003, a textbook on thermodynamics and statistical mechanics published by Wiley in 2014, and also 5 US patents. In 2014, Dr. Binek gave testimony before the Subcommittee on Commerce, Manufacturing, and Trade of the United States Congress, explaining how small solutions in nanotechnology drive big innovation. What the subcommittee members didn't know was that in his spare time, Dr. Binek played electric guitar in a rock band called Fluffy Psycho Bunnies. Among other gigs, the Fluffy Psychos played as part of the entertainment program of UNL's conferences for undergraduate women in physical sciences. Since then, Dr. Binek and the former drummer from the Fluffy Psycho Bunnies formed a new band called Prime Objective, which is just now preparing for their big comeback tomorrow as entertainers at a birthday party. Despite this critical juncture in his career, we're very fortunate that Professor Binek has found the time to talk about his work on voltage-controlled Néel vector rotation in zero magnetic field for our seminar. So please, Christian, take it away.
Yeah, thank you, Kirill, so much for this very kind introduction. And thank you and Shin in particular for organizing this wonderful Spintronics online seminar. I tried to listen to as many as I could. It was always a great pleasure. So today I would like to talk about voltage-controlled Néel vector rotation in zero magnetic field. And before I give you an outline of my actual talk, I would like to stick for a moment with just the title of the presentation, because it has some keywords that hopefully get some of the community here excited. Let's start maybe with Néel vector, which indicates that we talk about antiferromagnetically ordered materials. And in that context here, we talk about antiferromagnetic spintronics. Then it has the word voltage control, which has to be seen in contrast to control spin polarized currents via spin orbit torque or other means. And that means if we think in terms of devices, we have a chance to get to ultra low power devices. Also, the fact that we talk about antiferromagnets gives us a chance that those devices are fairly fast in terms of switching. And another big plus, and that is really the new component of this work, is that the switching of the Néel vector, the rotation of the Néel vector, is achieved now in zero applied to our own surprise, in zero applied magnetic field. And not in the title is the fact that, and that was the original idea for using boron doped materials, that we can go to fairly high temperatures which promise CMOS compatibility. So we have demonstrated this switching at least up to 400 Kelvin. So with that, let me go a little bit more into the outline of the presentation, because as a matter of fact, I would like to take you on a journey that reflects my own joy and pain related to this work, and of course that of many, many collaborators. And by the way, you will hear Kirill's name multiple times throughout this presentation, because his theoretical findings played a key role in various steps which brought us to this point. So all started out some longer time ago with the attempt to achieve Néel vector switching in exchange bias heterostructures, where the voltage active component of this exchange bias system was chromium oxide, a magnetoelectric antiferromagnetic archetypical magnetoelectric material. And I will talk about what we did in these systems, what we achieved, but then also what the shortcomings of this approach are. One of them was right from the start that the Néel temperature of this material for applications in CMOS environment is low. It has a Néel temperature of 307 Kelvin in the bulk, but that's not sufficient for those applications, as you know. And it was in fact DFT work done by Kirill, who proposed to do boron doping to increase the Néel temperature. And we did that, and we did increase, as predicted, the Néel temperature. But with that, to our own surprise, came multiple other changes in the system, some good, some not so good. And I will report on what we found there in addition, and what happened when we tried to use this material to do the spintronic devices, as first based on exchange bias, and then later on devices that have reduced complexity. So those devices with reduced complexity are Hall bar type devices, and it is in those devices where we could show that zero magnetic field voltage controlled Néel vector rotation is possible. I will then show that we also made a big effort to show that this effect or this switching effect we see in these devices, which is reflected in a change of the Hall resistance, that this is indeed a magnetic switching effect and not some other artifact. And for that, we teamed up with the group of Alexei Gruberman, and he, for example, did some atomic force microscopy imaging, and we had other independent measurements that show this effect is indeed magnetic in origin. And then finally, I will sum it up and conclude. So let me get started with an introduction that many of you may have seen before. I gave this kind of introduction many times before, but I think it's a good start to remind ourselves to the voltage controlled exchange bias and the important component in there, namely the magnetoelectric material chromia, the pure chromia. So here you see a fraction of that magnetic unit cell of chromia. You see the threefold axis, which we call C-axis. You see here two chromium 3+ ions and their respective spins up and spin downs. And you see their oxygen 2- environment, which is nearly octahedral, with some distortion that is exaggerated in this cartoon. But this distortion, in fact, is critical for the magnetoelectric effect. So let's see from the cartoon roughly how we can understand the magnetoelectric effect. So we apply an electric field. By doing so, the ions start to move out of their equilibrium positions to new positions because they experience a force. They do that. Of course, this motion is tiny, but it is sufficient to bring this chromium 3 plus I and A in this crystal field environment of this larger oxygen 2- triangle and this different spin species in the crystal field environment of this smaller triangle. So this has various effects. It changes the exchange. It also changes the G tensor. What it, globally speaking, does, it lifts the degeneracy of the sublattice magnetization, and so you no longer have a fully compensated antiferromagnet. You have a type of a small ferromagnetic moment, and in the linear regime, that means the induced magnetization induced by an electric effect is mediated here by this magnetoelectric susceptibility. Now, this magnetoelectric susceptibility, the sign of it depends on the domain state in which the system is. There are two 180-degree degenerate antiferromagnetic domain states. And in one of them, this sign is positive of the alpha, and the other one, the sign is negative. So that means that the magnetization in one domain you induce is positive, in the other domain it's negative. That in turn means if you now take the system and put it into a magnetic field, then you create a Zeeman energy of that induced magnetization in the field. And there's a difference in the Zeeman energy between these two types of domains because that sign of alpha here is different. And that is reflected here in this free energy landscape, free energy as a function of the antiferromagnetic order parameter. And you see here what happens to that former degenerate double well potential when you apply a product of electric and magnetic fields. You lift the degeneracy, and if you make that product big enough, then you can destabilize one type of single domain in favor of the other, so the system would switch over from one single domain state into the other. Notice that you here need a product of electric and magnetic field. And of course, you could reduce the magnetic field if you increase the electric field accordingly, but you cannot bring it to zero. Another important point I have not much time to talk about, but it's actually quite important for everything I say here. So you see, I make a little bit distinction between the bulk of the material and this pink part here on top. It is not at this point that we have deposited any other material on top of the chromia. It simply indicates that the surface of this single domain crystal is special. It carries a magnetic moment. And that is a finding that microscopically maybe came first from Jalushinsky, and then Kirill Belashenko put it in a symmetry-based general argument where he did show that if you have a system that is magnetoelectric or has the symmetry prerequisites that allow for linear magnetoelectricity to appear, then this system has this boundary magnetization as a consequence of that. At least that boundary magnetization is symmetry allowed. So that was a very important finding for everything that comes next. And just very recently, this year, there's another nice article actually to honor Jalushinsky. It came out by Nicola Spalding, and she just took yet another look at this problem of boundary magnetization, and she expresses this in an intuitive analogy, which we can look at as a bound charge in systems with spontaneous ferroelectric polarization. There you have at surfaces, you have bound charge, and she makes the point that in systems with magnetoelectric multipole decomposition, you will have bound or surface dipole magnetism. So all that is the same looked at from different angles. So we take this now and made exchange bias systems out of these materials that are affected by an electric field. Here you see a cartoon. So we have this magnetoelectric antiferromagnet. We put here a ferromagnet on top, which couples with the antiferromagnet by a quantum mechanical exchange interaction. This ferromagnet is perpendicular anisotropic. And now by applying an electric field in the presence of a magnetic field, a stationary magnetic field, we can now switch the exchange bias from one, let's say the ordinary negative, to the positive and back. I show this here in the cartoon. So this is a hysteresis loop of that ferromagnet, and you apply an electric field of one particular orientation, you get the ordinary negative exchange bias, but then you flip the sign of the electric field. And by doing so, in the presence of a magnetic field, you switch all the orientation of all the spins in the antiferromagnet. You 180-degree flip them. That in turn flips the boundary magnetization, and with that, the sign of the exchange bias changes, and you go to positive exchange bias. And now you see, based on this remnant states here, you can use that as, if you like, as a state variable, as bit information in devices. And this is a cartoon. Let me show now you our proof of principle in a system made out of a bulk magnetoelectric chromia, where we put a thin film on top deposited by MBE. And what I just showed you is happening here. You see a cartoon of the atomic and spin structure of Cr2O3. You see here this boundary magnetization, which again is an equilibrium property. So it's also present, that's a nice thing, if the surface is rough and has these steps here. It has been selected in a particular single domain state. So the exchange bias accordingly is on one side here. In this case, if the product is positive, the exchange bias field is positive. Now we can turn it around. We can change the orientation of the electric field. We invert the boundary magnetization, and by doing so, we change the sign of the exchange bias field. So the product here of the applied field is negative. The exchange bias field is also negative. These are actual measurement results we obtained in such a system, but as I said before, this was just a proof of principle in the sense that the antiferromagnet was a bulk single crystal. And then it took us quite some time, us and other groups in Japan, in particular, Tohoku and Osaka, to bring this effect into an all-thin film geometry. I will talk about this in a second. Before I do, is what allowed us to continue this research, where the potential to use this effect in memory and logic devices, but emphasis here being on memory. And you can see how this is going. So this is basically a fundamental building block here, this voltage controlled exchange bias system, where you have this voltage controlled boundary magnetization. Then it takes just one more element to make a magnetic random access memory out of it, so to say. You can put a tunneling magnetoresistance structure on top. So you have this free layer, which you can now read out by bringing it into this tunnel magnetoresistance structure. For this, you have to drive a current through the system to read out the contrast in the tunneling magnetoresistance. But the writing of the bit information is pure voltage-driven writing. If you happen to provide a symmetry breaking magnetic field in addition, you can try to implement that as a stray field in the structure of the device. But it is something the engineers certainly would not like. Anyway, once you have devices of that type, you can also go on and think about more complex devices in a CMOS environment. For example, colleagues at Buffalo University primarily did that together with Peter Dauben and others, and thought about structures like this, where you use the fact that inherent to this type of devices is non-volatility. So you set the bit information, and then you remove the electric field. And of course, the bit stays written because the antiferromagnetic order is imprinted in the system. And that is then useful to make latches or this type of flip-flop here, where you have this, what people call the instant on type of electronics. You can switch off your computer, basically turn it back on, and all the information is still there. There are a few ideas and patents. Some of us are involved here, so that got some traction and interest. But of course, now back to the real practical problems, and how implement that in thin film? Many groups started to work on this. I show you our results, which took us a long time to get there, and it also reveals some problems, which I want to point out in a minute. So here you see a chromium oxide thin film. It's not particularly thin. It's still 300 nanometers thick, but it's certainly no longer a bulk single crystal. And on top, we deposited a small cobalt palladium structured square. Why a small one? Well, that was already an insight, because if you make it larger, then of course you pick up all the potential defects that give rise to leakage. So in this sense, scaling here is your friend. If you make things smaller, you can combat leakage issues that appear in thin films to some extent. Here this is not a very small structure, so 90 by 90 microns, so we still used magneto-optics to read out the magnetism of this ferromagnetic film here on top. We used a polar Kerr effect, and we took Kerr loops. And here is one loop, so your system, see the system has been prepared in a system of positive exchange bias. And now we apply a magnetic field and a particular negative voltage to turn the system back into negative exchange bias. But you see, for quite some voltages, nothing at all is happening until you hit that critical product of electric and magnetic field, where the anisotropy barrier of the antiferromagnet can be overcome, and then the antiferromagnet is reversed by 180 degrees, and the exchange bias indeed flips, and we get negative exchange bias. In this geometry with this thickness, it happened here at 9 volt for this applied magnetic field. Okay, so far so good. But what are the problems with this entire approach? Well, there are some shortcomings I would like to point out. First of all, and I guess we have heard that quite a bit in this entire seminar series, there are some problems intrinsic to ferromagnetic spintronics. If you want to reverse a ferromagnet, which carries your bit information, that takes time. It happens on a nanosecond time scale associated with the precession frequency of the ferromagnet. That's a problem if you want to beat CMOS, for example. And also, maybe even more of an issue, it takes energy to flip the ferromagnet. And in addition, and I don't go into the details, but by now there are actually multiple manuscripts that discuss this in more detail. If you start to scale down your system, roughly speaking, if you reduce volume from the antiferromagnet, you find that the interface effect, the interface interaction, starts to play a more and more of an important role. And that breaks a symmetry in this whole system, in the sense that switching in one direction, guess what? The direction I show you here is easier than switching, far easier than switching back. In one direction, so to say, the exchange interaction supports that switching. In the other direction, it hampers it. So if you make your system thinner and thinner, these effects that come from the interface become more and more pronounced. And that's bad, because it means the system is not fully scalable to ever smaller sizes. Then, of course, the generic problem with the utilization of this magnetoelectric effect in terms of switching, you need a magnetic field. You need the EH product to activate this switching effect. That's not good, because it's difficult and not wanted to implement this permanent magnetic stray field, let's say, in a device. And last but not least, that actually was one of the things the industry pointed out very early on. The Néel temperature of 307 Kelvin of chromium oxide is not sufficient to make a functioning device, especially not in a CMOS environment. It turns out that all of these problems can be addressed by boron doping. Interestingly enough, we started the boron doping business to address this problem, but the other problems will also be addressed as I show during the next slides. So what is the boron doping doing? Let me first start by why we started it and where it comes from. So it came from the request of the industry to increase the Néel temperature, or fundamentally speaking, of having an interest in figuring out what happens how can you do that? How can you change the antiferromagnetic ordering temperature? And Kirill Belashenko and company did a comprehensive study on what you can do by doping the system. And the conclusion of this manuscript was that boron doping, so replacing particularly the oxygen by boron, gives rise, of course this is rather involved, so there are edge states that then hybridize with the 3D of the chromium, and that in turn affects the exchange between the chromium ions, and the exchange energy affects the energy it takes to flip a spin, and that in turn affects the antiferromagnetic ordering temperature. And we picked this idea up and asked ourselves, how can we do that? How can we dope? And the idea was then to grow these films by pulsed laser deposition in the background of boron, decaborane gas. And we did that, and indeed we created nice films. And when you do magnetometry on these films, you can pick up a residual magnetic moment. It's a weak magnetic signal from not 100% compensation, and that moment is directly a proxy for the antiferromagnetic order. And by doing so, we could show that indeed, as predicted, we could increase the Néel temperature. Then we brought our films to our colleague these days in the context of C-spin, to Paul Wolf, who then did his wonderful high-angle annular dark field transmission electron microscopy investigation. And here you see one of his results on one of our boron-doped films. What you can see here are only the high Z elements, the oxygen and the boron. The method is blind, but you see the nicely arranged chromia. And what always surprises and amazes me is you see actually the buckling structure of the chromium 3+ ions, how they are sandwiched between the here invisible oxygen 2- layers. So the message here being is, despite the impurities, despite the doping, the films are actually very nice structurally. And now, of course, we were naive and we said, okay, we got it. We have the increased Néel temperature. Now let's make perpendicular exchange bias systems with them. And that gave some interesting and some frustrating surprises. So first of all, when we tried the perpendicular exchange bias, try to make the story short, we found absence of exchange bias. There was no significant pinning, but we did see loop broadening at what people call the blocking temperature, which was above the 307 of pure chromia. So what that means is, yes, the system was all magnetically ordering significantly above 307, and yes, there was interaction between the ferromagnet and the antiferromagnet, but it was just not a system that was able to pin the ferromagnet on its reversal. And then in turn we said, well, that may have something to do with the orientation of the boundary magnetization. Maybe it's no longer fully perpendicular, maybe it's somewhat tilted. And indeed, we grew in plane anisotropic, actually the regular exchange bias systems, and we saw exchange bias coming back, even sizable exchange bias coming back, but not at the temperatures that were beneficial in the sense that the doping made sense. So the exchange bias pathway was basically done for the boron dope material. Bad news at the time, but we learned something. We learned that the boundary magnetization doesn't have to be necessarily fully perpendicular. There can be tilting, and there most likely is tilting in the boron doped systems. And we also learned from IV curves, from transport measurement, that the boron doping had a surprisingly positive effect on the leakage. It reduced it rather than increased it. So you see here the currents for applied voltages in the IV curves are lower than they are in the pure chromium. So that kind of forced us to a new path. But before I go there, there's one, and this is not historic, but I put it now into this context of new effects from boron doping. So another effect that comes with the boron doping, fully surprisingly, is induced polarization. And this is a collaborative approach together with Alexei Gruverman here, also from the University of Nebraska-Lincoln. And he uses, among other scanning probe microscopy techniques, he uses also piezo and force microscopy, which is a version of an atomic force microscopy that is sensitive to the mechanical displacement of material due to a piezoelectric effect. And that piezoelectric effect is always there as soon as your system has some polarization. So we can measure local polarization via this piezo force microscopy, via the electromechanical response. And if we do that on boron doped material, we find a rather surprising result if we go through such a hysteresis loop. So you apply a voltage locally to the system. You find this in the phase of the signal, you find this hysteresis, which for the experts in piezo force microscopy looks exactly like the signal you would get when you measure a ferroelectric system, a system that has spontaneous ferroelectric order. And similarly, this butterfly-shaped effective piezo response coefficient is indicative of what people would immediately say, oh, that looks like a ferroelectric response. However, if you have a more careful look, you see that this response is not permanent. It decays over time, slowly here on a multi-second time scale, but it will decay. So the system did not turn into a ferroelectric material. All we see here is a transient effect. It is a strong induced polarization, but quite unusual. But I stress is that it's not a spontaneous polarization because the system did not turn into a multiferroic. We still have only one true order parameter here. And as a control experiment, we did the same, or Gruberman did the same piezo force microscopy on pure chromium films grown by the same method, and there this effect is absent. So a few thoughts about what can cause this induced polarization. And our explanation are so-called polar nanoregions, which local polarization, which gets aligned in the presence of an applied electric field. Now then, the next question is, where do those polar nanoregions come from? And the candidates are the exact same boron chromium 4 tetrahedra that give rise to the actual TN enhancement in this material. And it was, again, my colleague Paul Voils, who did Eel's electron energy loss spectroscopy combined with DFT to identify that indeed these tetrahedra are present. That's why the TN is enhanced, among other things. So not all boron, by the way, goes to the site where it should be, but a good fraction goes there. And those then create also local dipole moments, which in the presence of an electric field can be aligned to give macroscopic polarization. We come back to this in a minute. Now I want to show you, if we can't do exchange bias systems, what else can we do? And it turns out we can create devices with reduced complexity, get rid of the ferromagnet on top. Don't worry about pinning. Just read out the boundary magnetization directly. And a way to do that has been established already in pure chromia with the help of Hall resistance measurements. So first, I want to show you data. In this case, I show you our data measured on pure chromia. But there are other data, for example, from the group in Dresden, Kosup and others, did the exact same type of experiments and came to the exact same conclusions. So if you have a system like this, oh, sorry, you have your chromia thin film, you deposit a Hall bar of a heavy metal here on top, platinum in this case, and you drive a current through it and you pick up the transverse voltage, a Hall-like signal. What you do is you probe the boundary magnetization, which in turn is a direct fingerprint of the underlying antiferromagnetic order. And this is what we see here in our own system. When we prepare the system by applying a magnetic field on cooling and then heating up, we can select one domain state over the other. And if we do so, we can have the order parameter in one particular direction, and with that, the boundary magnetization in one particular direction. And we see here basically the temperature evolution of the boundary magnetization for both single domain states. And of course, that signal disappears as soon as you go higher than the antiferromagnetic ordering temperature. And similarly, it's also interesting to look at the magnetic field dependence of that Hall signal. It turns out if you are at temperatures significantly below the Néel temperature, the magnetic field dependence of that Hall signal is very weak. And if you come close to the Néel temperature, you get these pronounced S-shaped curves. This is something to keep in mind in a minute when we look at the boron doped systems. So that's what we do now. We rather than using the pure chromia system, we use the boron doped chromia, but put it in the same type of Hall bar device. And notice also we are able to apply a voltage across the thin film of boron doped chromia. Because we deposit this material on a gate electrode, in this case vanadium oxide, which is an oxide but metallic at this temperature. And so we can apply a voltage. Here you see the optical image of the resulting lithography of that Hall cross. And now I show you the interesting results. So maybe we start with the bottom here. You see an inset. The inset basically tells you here that we changed the electric field and that we could reach threshold electric fields where we switched from one state to the other. And here we had a magnetic field applied. Why? Because I told my postdoc, apply a magnetic field, because the only reason why the system should ever switch is the magnetoelectric effect. And without a magnetic field, you will not observe a switching. So he did that. He observed the switching. Here you see the hysteresis curve. Here you see another experiment where we are in one state, take 100 measurements, then apply an electric field and the magnetic field that is always applied, switch into the other state, measure again 100 times without the field, apply the field again, switch back, and so forth. So we were happy. We thought we do what we typically would do in pure chromia and what the group in Dresden actually has also shown in chromia. But then I said, so now let's investigate. Let's show that when we remove the magnetic field, we should accordingly increase the electric field, that otherwise the switching doesn't happen. And then my postdoc reported something very strange. He said, I don't see any change when I change the magnetic field. So I got angry and said, well, you don't see a change. Then why don't you switch off the magnetic field? Then you will. And he did that. and indeed, we still saw the exact same switching, no effect whatsoever. So what happens here is you apply one voltage, no magnetic field whatsoever. You apply a voltage, you switch from one state into the other state, You remove that voltage, the system stays in this state. You measure 100 times or how often you want. Then you switch the voltage of the other polarity. You switch back. You can take measurements and so forth. Okay, so let me compare this finding with what happens in pure chromia. So we have the results, for example, from the Dresden group in pure chromia, and we have our results in the boron doped system. This is what the guys in Dresden did. The same type of structure, a Hall bar of the similar type on top, and they measured the Hall signal in the presence of an applied magnetic field of 1 Tesla. They changed this gate voltage, and by doing so, they switched the Hall signal symmetrically between negative and positive values. Why? Well, because the antiferromagnetic order parameter switches from up to down, and so switches the sign of the boundary magnetization and the sign of the signal. So that is a clear indication of 180-degree switching of the order parameter. Now, what happens in our system? Well, if one looks more closer, one sees a very obvious difference. We are not switching the Hall voltage and therefore also not the Hall resistance between symmetric values. We switch between a value that is almost 0 and a value that is non-zero. And this is already a clear indication that the states between we switch are not just 180-degree degenerate. We think that is the clear fingerprint that this is a 90-degree switching, which makes the interpretation also much easier in the sense that if you would have to explain a switching of the remnant state and the remnant boundary magnetization by 180-degree in the absence of a field that breaks time inversion symmetry, that's already a problem. But if we switch 90-degree, we don't have that problem. So that was a clear indication in this direction. Okay, now the next is I want to show you, we wanted to make sure that this is really a magnetic effect and not just some artifact. First, we did what we can do. We looked at transport data and tried to figure out how can we show that this has something to do with magnetism. Well, we measured the magnetic field dependence in these different states. So first, we switch it into a state where there is a significant Hall voltage, very similar to the situation in pure chromia. And if you do that, very similar to the situation in pure chromia, you hardly see any magnetic field dependence because we are here at room temperature, which is substantially below the Néel temperature of boron-doped chromia. Now we switch the system into that 0 type of voltage state, and we see suddenly a difference. We see a very significant field dependence. By the way, these scales are made in such a way that you can direct compare them. So it's not that one is artificially blown up with respect to the other. So here is a magnetic field dependence, here it is not. So our interpretation is here we have the system in a state where the antiferromagnetic order parameter and the boundary magnetization is primarily normal to the plane. Here, the antiferromagnetic order parameter is in the plane, and therefore the torque on the magnetization is at maximum, and therefore we see, if you apply a magnetic field, and therefore we see a field dependence of that signal. Okay, but more convincing would be a completely independent measurement, something that has nothing to do with our transport data, and there we teamed up with Alexei Gruberman, who does also magnetic force microscopy. And here you see an atomic force microscopy image of our Hall bar, here magnified. You see that leg. And now you see what happens in the magnetic force microscopy contrast. When you apply positive voltage, the contrast disappears. And when you apply a negative voltage, the contrast reappears, and so forth. That is another indication that indeed this effect, the signal we see, is magnetic. But Alexei wanted to be very careful and wanted to make sure there are other potential artifacts. So he said there could be charging effects. So he measured Kelvin force microscopy in addition. And the Kelvin force microscopy, which basically measures the surface potential when you scan across this leg here, was identical no matter what type of voltage we applied. So we could exclude charging artifacts, and therefore, indeed, this signal is magnetic. Okay, now I come to more or less to the end. So I would like to now discuss what we think is the mechanism that gives rise to this 90-degree rotation. So here's the chain of events that happens. We think we have local strain due to the fact that there is random substitution of the oxygen by boron, which creates this boron chromium 4 tetrahedra with boron displaced and creating local nanopolar regions. Now, if you apply an electric field to that system, these existing dipoles, similar like dipoles in water, would orient with the field and create a macroscopic polarization. Now, this macroscopic polarization has a piezoelectric effect. It creates a piezoelectric response, epsilon delta L over L, which is given by dZz times E, and electric field. So, and this piezoelectric response, this creates a strain, and this strain affects the magnetic anisotropy. Why am I confident about the fact that the strain affects the magnetic anisotropy? Well, there again is extensive work done by Kirill Belashenko's group on exactly that, namely how strain affects anisotropy in pure chromia. Granted, okay. So based on that, we assume anisotropy. By the way, it's worth to mention also, you can read this in this paper, that the anisotropy of pure chromia is already quite weak. So it doesn't take much to change that. So, and then we think that the change in strain changes the anisotropy. The change in anisotropy changes the landscape of the anisotropy-free energy and allows then switching between different local minima, and that gives rise to the Néel vector rotation, not switch by 90 degree. Okay, my last comment is about switching speed, which is of course also important, but not yet experimentally studied by us. But we have collaboration here with theory with Chalou, and she basically based on a LHE type approach, she comes up with an equation of motion motivated by a spin torque driven reorientation of the order parameter, but she can use the same formalism which can be translated into the formalism of an inverted gravitational pendulum. She analyzes that by putting in the actual numbers, the material parameters of chromia, and she finds that a switching speed of 100 picoseconds should be possible, which is decent. So with that, I would like to conclude. So what I've shown you is that boron doping does a couple of things. As initially proposed and expected, it increases the Néel temperature as we wish. It gives, unexpectedly, it gives rise to induced polarization, quite a significant effect. And because of this effect, we were able to create this complexity-reduced devices where we can show rotation of the antiferromagnetic order parameter by 90 degree in zero magnetic field. That's the important point here. And this can also be done up to 400 Kelvin. Here is actually a data point at 400 Kelvin, not so beautiful, but at least there still is an effect. And I showed you independent evidence that this is indeed magnetic in origin. And a few words about the switching speed. So there's a theoretical estimate about the switching speed. It's also worth to mention that this system is not a multiferroic system, and the absence of spontaneous ferroelectric polarization can be considered positive, because in systems such as BFO, for example, where you have ferroelectric order, it is the ferroelectric order and the hysteresis that comes with inversion of the polarization that is detrimental to energy and speed. So with that, I really stop here and acknowledge my collaborators in this particular piece of work here my group, my postdoc Atta Mahmoud, my student Will Echtenkamp will hopefully graduate on Tuesday. Jun Lei got a faculty position now in China. Alexei Gruberman, he was responsible for the MFM and PFM and Kelvin probe microscopy. Peter for everything in terms of spectroscopy, and Chalou did this and company did this theory work. And here my sponsors. And okay, finally, thank you for your attention, and I'm open for questions.
Hey, Christian, thank you very much for your talk. We can now take questions. So please raise your hand in Zoom if you have a question, or if you're in Twitch, just type your question in the chat box. Wei Yuan, please go ahead and ask a question.
In your page 10, you measure the Hall signal at the high temperature. So why the Hall signal is nonlinear at 330 Kelvin?
Yeah. Okay. So first of all, let me say the following: the entire discussion about what creates this Hall signal is actually not a done deal. The favored theoretical answer to that is it's a spin-Hall magnetoresistance effect. But there are other effects, especially when it comes to heavy metals on top, which have high Stoner polarizability, such as proximity effects that could explain Hall voltage contribution as well, and other effects even. So that is still not fully understood. The only thing everyone agrees on is that it's a probe for the order parameter. Now, why do we have a signal at all at high temperatures? Good question. I would argue the following: if you apply a magnetic field, you certainly induce magnetization also in the chromia, simply because it's a paramagnet. It has paramagnetic susceptibility. You induce magnetization, and you induce also magnetization at the interface, very similar to the presence of boundary magnetization, which would depend on.
But the temperature is higher than new temperature.
Yeah. But that doesn't mean that the susceptibility is zero. In the contrary, if you have an antiferromagnet and you look at the parallel susceptibility of the antiferromagnet, if you are above the Néel temperature, that doesn't mean the susceptibility is zero. On the contrary, the susceptibility even maximizes slightly above the Néel temperature. So you can induce magnetization in a paramagnet with short-range antiferromagnetic order, even if you are above the ordering temperature. And it is, I would argue, that it is this induced magnetization which then also contributes to some magnetization at the interface, and then the whole argument starts over again, and you can have a Hall signal, wherever that comes from. It still can be spin-Hall magnetoresistance, it still can be proximity, it can be a mixture of both.
Okay, thank you. Thank you.
Thank you. Stephen Bennett, please go ahead.
Hi, Christian. So have you measured the leakage current as you apply voltage to your gate?
Yes, we did. Let me try to, I showed you this tiny plaquette here. These are actual data from our films. I mean, this doesn't tell you much unless I give you the numbers of the electrode sizes, which I don't have handy. But well, in this case, we had a prefabricated Hall bar, and just used the Hall bar as one electrode, so to say, the cross, and the entire bottom as another electrode, and then apply this type of voltage across this structure and measure these currents. So yes, there's leakage. there is also breakdown, and you are always at the edge of losing your sample, because somewhere there might be a region, a grain boundary, which turn out to be prone to leakage. The grain boundaries have been shown in DFT to have reduced a band gap and are actually prone to leakage. And if you have such a grain boundary under your electrode or multiple, then you can have the system can burn up. So these things quickly grow out of, exponentially grow out of proportion, and then it dies.
Okay.
Have you considered whether this leakage could contribute to some of your resistivity changes across your Hall cross? And while they're joule heating and
Yes.
current paths could be created, but I feel that once you get those high frequency or switching speed measurements, it could definitely put those questions to rest on whether it's antiferromagnetic switching or the latter.
That's right. So first of all, the answer is yes. This question was gave me nightmares and was on the top of my list, especially because there's the manuscript by Jeffrey Breach from MIT, who has shown that in some systems, nickel oxide and platinum, I think, in their analysis, there's effects that are due to ionic migration. Now, having said that, within this seminar series, there was a presentation by Matthias Kloy, if you go all the way back, number 37 or something like this, who I think he got the same question, and he could show, he looked at this problem because it affected his work also, and he found out that already in nickel oxide system where the MIT group thought it's all an artifact, that it's actually a mixture of both, and that the majority of the switching effect was indeed a magnetic effect, and only a fraction of the effect, a creep type fraction, came from a current-driven motion of ions. Now, in our case, this is exactly the reason why we teamed up with Gruberman, and we wanted to make sure that we have a method that is not dependent on this transport data that can show that the effect is indeed magnetic. But we are not stopping there. We go on, and we just today formulated a beam time proposal. And of course, we want to see directly the rotation of the order parameter by XMLD. And similarly, I want to see the rotation of the order parameter by XMCD. So that's next. And in addition, we also don't stop by using a magnetic force microscopy in the conventional way. We also team up with colleagues who do now this advanced method of nitrogen vacancy scanning probe microscopy. There's a group in Zurich we are in contact with, and locally we have our colleague Abdelghani Laouraoui, who is doing NV spectroscopy, and we teamed up with him already to learn more about what is going on here in particular. So that's it's a very important question. Yes, I agree with that. But
Thanks, Christian. That sounds great.
Okay, thank you. Emra Turgut, please go ahead.
Thank you very much. When you mention 180-degree rotation of antiferromagnetic order, do you mean 90-degree rotation or 180-degree rotation of the magnetoelectric effect, or 180-degree rotation of interfacial uncompensated moments?
Okay. I hope that wasn't too confusing. Let me come back to this. I talked about both. So the point being that in pure chromia, the textbook archetypical magnetoelectric material, chromia, if you apply an electric and a magnetic field to that system and you overcome the critical value, you indeed switch the order parameter by 180 degrees. And you can do that because you apply electric and magnetic field. And that is without question, that is long known. That is known for 60 years or longer. So that's not a question, that happens. In our system, in the absence of an applied magnetic field, that would be hard to understand. And indeed, from what we observe and how we interpret it, we think that what happens is that it's not a 180 degree rotation here, but a 90 degree rotation of the order parameter and of the boundary magnetization. And what is the end? I lost my train of thought, but yeah, it's a 90 degree. Okay. What is important also to stress here, the thing that immediately follows from the fact that we do this without a magnetic field, the one thing is clear. The switching, whatever it is not, I repeat, is not switching based on the linear magnetoelectric effect as we know it from chromia. That's not what it is, right? That's why I presented this explanation in terms of polarization, strain, change in anisotropy, and then change of easy axis due to change in anisotropy.
Okay, thank you.
Okay, Wei Yuan, please go ahead.
A quick question. So I think you manipulate the magnetic switching in bulk and thin film. So I'm wondering if you are in the electric field at the same order or different.
The last part I didn't guess. You wonder what?
So I'm wondering if you use the same order electric field or very different electric field to manipulate thin film and bulk.
So you mean in terms of magnitude or?
Yeah. So you use the electric field to manipulate the switching in film and bulk. Is the electric field at the same order?
Oh,
yeah.
Yes, it is. Yes, it is.
Okay.
So let me speak for chromia. There's easier. The answer is a little bit trickier. So I always tell you that it takes a product of electric and magnetic field to switch the antiferromagnetic order parameter. And that is true for bulk and film, as long as you can ignore what happens at the interface energetically. If the interface plays an ever-increasing role when you make the film thinner and thinner and thinner, then it's no longer that simple that it's just the product of the two. Then there are additional energy terms that change that a little bit.
Okay, so that means even in the thin film, there's no any leakage? So when you get to the film, so it's leaking or not?
It's whether it's leaking. Are you asking? Yes, it is. But that's a different problem. That's let's say a technical problem. So you could say if you only could improve and improve and improve the growth of the thin films, that problem can be solved. And that is true. Over time, we made better and better films and the leakage gets down. So that's a technical problem, an engineering problem, while the asymmetry in the switching that happens relative to bulk when you make your film thinner and thinner, it's not a technical problem, it's physics. You can't avoid that.
Okay, got it. Thank you.
So let me also ask a quick question, Christian. So in this experiment that you're showing on the slides, so what determines the sign of the whole voltage? And also, is it at all important that chromia is in a single antiferromagnetic domain state, or can it have domains?
Yeah, good questions. So I guess you wonder, rightfully, why do I switch between up and in plane why not between down and in plane, right? So, and if I would do that, I would not switch between 0 and minus, I may switch between 0 and plus, for example. And indeed, that happens. It does happen. And also it sometimes happens that the switching is not fully pronounced, but you get stuck somewhere. Both happens. So the getting stuck somewhere, I would interpret as a domain state, and the switching of the other type, I would interpret like you switch rather than switching between, let's say, up and in plane, you switch between down and in plane. Now it turns out, and I don't know why that is, that these things are not fully symmetric. So what I show you here happens by far more frequently than the other. The other does happen, but not as often. Why? I don't know.
Have you tried magnetoelectrically annealing everything before doing the experiment?
That's a big problem. The short answer to is if I do that, the sample is dead. Because the Néel temperature of the system due to the boron doping is so high that when I magnetoelectrically anneal and want to go above the Néel temperature, I come to a temperature, at least that's our interpretation, where the boron starts to diffuse and changes irreversibly the actual structure and behavior of the film. This is, by the way, another thing we are currently studying. So we have a collaboration with NIST going on. They did neutron profiling, and they did exactly that. They looked at the boron, so they are sensitive to boron, and they looked at the boron profile with neutrons of our samples on exposure to ever higher temperatures. And they see, if you go to higher and higher temperatures, they see that this profile changes and it looks like the boron is moving towards the surface. So in other words, we cannot do that experiment if we don't want to lose the sample. Now, having that said, we will do this experiment now to conclude on the neutron data together with our transport data and try to make sense of both and see what's happening.
All right, thank you very much. So I don't see any further questions. So let's thank Christian for this interesting talk.